Hello again. I'm glad we have another chance to talk about geology. Geology is a historical science. And of course, to talk about history, you have to know dates, you have to know ages. To be able to compare events, you have to know what occurred at the same time. And we have three main ways of finding out ages within the rocks, within the fossils. The one that gives us the numbers is radioactive decay, the decay of radioactive elements, their isotopes. And particularly famous are uranium and carbon, but there's many other elements that do, and we can use those to determine dates that rocks formed. Another way we've been doing basically since the late 1600s, but big time since the late 1700s, is based on the law of superposition. You remember that, where a sand layer forms and a mud layer comes on top and then a limestone, and we go older, younger, 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 and then we look at the fossils. And well, this fossil is older and looks different than this one, which is younger, and then we can correlate off of those. You know, for example, here in Santiago, I can take you out to the beach cliffs here at Torrey Pines. I can show you some snails that are about 45 million years old, but I can also show you the same snails in sedimentary rocks around Paris, France. Same snail, different parts of the world. We would say they were alive, roughly speaking, at the same time, and there we are beginning to put together a worldwide picture of things going on. And the third way we do this is basically on reversals of the magnetic poles. I mean, here in our lifetimes, we're used to the magnetic pole being up at the north, but it switches from north to south and back and forth again in a totally irregular pattern. For years, people have tried to write equations to define when it switches from one to the other, but it doesn't. And the beauty of that for us is, as historical scientists, is it gives us an irregular pattern, and we can compare them from different areas to, again, zero in on ages. So what we want to do now for a beautiful place here like Mission Trails Park, we look at that and we see all that beautiful geology, but it's the product of events at very many different times. And what we want to do tonight is try to sort that out a little bit and say, well, what did Mission Trails look like at different times? And that's what we're going to work on. And the earliest history, and we're going to talk about this in some detail right now, it's going to be a mountain building time. And you see the times there. When we look at these things here, this is from the back cover of the geology book at Mission Trails, and it shows the history in 4 different times. And what we're going to look at first is a lot of igneous activity, a mountain building time. And what we're going to see here that comes from, specifically, all that volcanic rock, that plutonic rock, all that magma that's in this area here at that time came from subduction of the Farallon plate. Now, Farallon plate, this doesn't directly pertain to what we're talking about here. I only put that on the screen because I wanted to introduce the terms Farallon plate. For California, there is no Farallon plate anymore. It's been dragged underneath California and it's gone. But I want you to remember that it's the memory of it, because that, dissolving some of that plate, is part of what's in the mountains in Mission Trails. Now, if we go to the full screen here and look at the map, you can look there on the yellow Pacific plate up by California where it says San Andreas Fault, and then look just to the above that there where it says Juan de Fuca plate in red. Well, that's a remaining piece of Farallon plate that hasn't yet been pulled under Canada. And if we go to the south of California there, still in the yellow of the Pacific plate where it says Cocos plate, pointing at that gray plate there off of Mexico, Central America, well, that's another piece of Farallon plate that still exists. But for us, in between, we're marked by the San Andreas Fault now. We don't have the spreading center anymore. North America has moved westward and run over the spreading center and causes a whole lot of mischief, a whole lot of changes here in Western North America. So here I've just colored in orange the oceanic lithosphere, that which is being subducted. It's being pulled down underneath the continent. And you see there that word asthenosphere. Remember talking about that asthenosphere? That's where rocks are heated so hot, they're not liquid, but they don't just sit in place solidly. They flow, they move. And when that subducting lithosphere, when that orange-colored plate here punches into that asthenosphere about 60 miles depth, it brings down water, seashells, things that aid melting, and then magma forms there, rises up about 60 miles, is contaminated or changes while it's rising, and it gives us the rocks that we see in our Mission Trails mountains. So in terms of plate tectonics, as regards mission trails, what's really important is subduction of Farallon plate. Now, in this little cartoon here, I want to discuss it a little bit further. Now, this says 120 million years ago, but think of it as a snapshot. I mean, the subduction is going on like a moving picture, and here's a snapshot at 120 million years. So in the schematic cartoon here, there's the downgoing plate. It hits the gray asthenosphere, and then the magma rises up, and a lot of the pods are showing there. Those would be masses of magma that cool beneath the ground and make plutonic rocks. And then all the way up at the top, there's some that makes it to the surface, and there's the volcanoes. Now, so that's vital to us. I think the first thing people think of when they visualize the landscape in Mission Trails Park are the mountains. Well, there's where they formed, and there's part of the time they formed. But let's go back. Let's go back 120 million years. Let's go to Mission Trails Park, and if you were standing there 120 million years ago, what would you see? Huge, explosive, volcanic eruptions. This happens to be Pinatubo in the Philippines in 1991, but this could just as easily be Mission Trails 120 million years ago. And if we look at Pinatubo farther, just look in that huge, wide-spreading gray cloud. That's full of bits of volcanic rock, that's magma, that's ash, that's gases, and you see that cloud spreading out over the landscape, and what's happening within the cloud to all those heavy particles? They're settling out on the ground, and they're going to accumulate as layers. Kind of like just what we see here at Mission Trails Park, and here right next to the exact border of Mission Trails Park, the quarry there in Mission Gorge. You look at all those layers, you see bigger layers, you look within the layers, and you see smaller layers, and there's 126 MA up there. MA meaning mega annum, in other words, million years. When did that material solidify, fall out of the sky, and gather there? 126 million years ago. If we look at it a little closer, you see that within the layers there are smaller layers, and you kind of visualize within that big cloud of pyroclastic volcanic material like we saw there at Pinatubo, it's not homogeneous. And what you see then are different kinds of layers. Finer stuff settles out, then some coarser, and it just builds up this whole sequence of older things at the bottom and getting younger as we go up to the top. And when we look at it up close, what do you see in there? You see, look at all the little pieces. All the pieces, that's stuff that was floating in the air that came settling out, just like we saw with that cloud there in the Philippines back in 1991. You know, next time you're around some of this, what we call Santiago Peak Volcanic, these lightish green, huge boulders they use for riprap, like, you know, the Mission Bay Jetty and various places, stop and look at them a little more closely, and you can see all the broken pieces that were broken during that explosive volcanic eruption way back when. Some of them there with a quarter for scale, you can see some of those broken pieces again. Well, let's move on now to that magma that didn't have the opportunity to make it to the surface. So here we are with a southerly view. We're here at the landfill by Highway 52, and you're seeing the 5 most famous peaks here stitched together in this phenomenal image of the main 5 peaks of Mission Trails Park. And these now, of course, are all plutonic rocks, which means what? All that you see there is something that had cooled about a mile below the ground surface, but look at that. Now it is the ground surface. If we look a closer look at some of these things here, there's the 118 MA up there. So here we are, like what I like to call the climber's wall here in Mission Gorge, and that means that the Monzo granite, the plutonic rock you're looking at there, solidified 118 million years ago. So when we look at Mission Gorge here, and you look at that, I like to call it our own little small-scale Yosemite, these beautiful sheer walls in Monzo granite. 118 million years ago, that was magma deep below the surface of the ground. Now, from the terrace here at the Visitor Center, we're looking over towards Cowles Mountain, and as everybody is well aware by now, that's one of the greatest hikes in San Diego, is go up and down Cowles Mountain. And I look at my calendar and see that I literally have, on more than 1,000 days, walked from the top to the top and back down on Cowles Mountain. But I'll tell you, I was walking so fast, I didn't slow down and look, and I didn't really realize until starting this project that the rocks up at top, look how much younger they are. 14 million years younger than the rocks near the base, and yet they look very, very similar. Now, what I'd like to do here is sort of demonstrate Omaha. I'd like to sort of demonstrate, when we think of these magmas, you tend to think of the magma rising up like this, and I do this myself. Use the lava lamp as an example of things rising up. But look what we have here. Here we are, here's our main Cowles Mountain like we're looking at in Mission Gorge, and it's 118 million years old. How do we get 104 million coming up along next to it over on top of it? So what means it didn't come straight up all the way, it must have gone laterally. And one of my favorite national parks in the world gives us a view of what might have happened. And mind you, all this is taking place deep below the ground way back when. We're just seeing it exposed now. But let us go south and take a full screen view of, to me, one of the greatest national parks in the world. For the U.S., when you think about iconic national parks, I think the ones that come into mind right away are like Yellowstone, Yosemite. Well, Torres del Paine here in Chile is, I would put it right up there in the same caliber in terms of its uniqueness and specialness. But what I want you to see here first, you notice a lot of gray rocks around. Those are 79 million year old dark gray mudstones. Much to my delight, I lead tours for the Smithsonian Institute, and to my delight, when I walk up to those, it's like an old friend. In those gray mudstones, 79 million year old mudstones, there are Inoceremus clams that look exactly like the ones in the sea cliffs at La Jolla Shores. Seeing an old friend. But what has happened here, though, if you look over on the lower left, there's the light colored. That's 13 million years old, and it's granite, pure granite. And if you look at it from the lower left corner and start following it up, look how it turns and turned back when and flowed more or less horizontally, injecting into the rocks rather than simply flowing straight up to the surface. So that doesn't mean that is what happened at Cowles Mountain, but I'm going to suggest that, well, here is a significant possible scenario. Since it happened there in Chile, it could easily have happened up here as well. So now the world's going to change on us. The plutonism, the magma is stopping. And the reason why, and we need to discuss that a little bit, is the angle of subduction of the Farallon plate changes. So when we look at the cartoon now, the drawing, so here's the same drawing, but you notice the subducting plate now. It was going down at a real steep angle like this, and now you notice it's going at a much more shallow angle. So if you're looking at the brown subducting Farallon plate there, when is it going to hit the asthenosphere as it's drawn here? It won't hit the asthenosphere until we get inland to something like, in today's terms, like Arizona or New Mexico, and then we do have volcanic rocks of those ages there. So what happened to cause the subduction angle to shallow? It was steep, and then it progressively shallowed. Well, look at it this way. If here's the spreading center, and these are volcanoes, so here's magma, here's a lot of heat, here's rock that's expanded by its heat, and then the plate pulls away. The farther away it goes, the colder it gets, the denser it gets, so if it subducts, it goes down at a steep angle. But as North America moves closer to the spreading center, and now you have warmer rock here, the warmer rock doesn't sink as easily, so it sinks at progressively shallower angles, and it's that shallowing of the angle of subduction that basically shut off the igneous rock, shut off the magma supply to make igneous rocks for mission trails. And so once we stop having magma be formed and rise here, what takes place? Erosion. It was going on anyway, but now it doesn't have to fight mountains that are building. It has the whole scene to itself now. Just erode, wear down, destroy the mountains that have been built in the last 30 million years. So we're now going to look at erosion, wearing the mountains down. Now, in this particular diagram here, we're starting off there with a photo along the base. That's a David Cooksey image there, where he's put together several images, and those are the actual mountains you see. And then on top of that, I drew something that's 100% fantasy. All I'm trying to do with that is say, those are plutonic rocks. They formed deep below the surface, so they used to be tall mountains up above it. I have no idea what they look like because they've been destroyed. So I just tried to draw something in there to give you the idea that our mountain tops are actually mountain centers. We're down deep within mountains. We're not simply looking at the tops of the mountains as they were when they formed. Now, you'll find this the next time you're at the Visitor Center in Mission Trails. They've commissioned a series of sculptures like this, which are on the railing outside on the Visitor Center, and this is trying to show that. You notice in the upper left there it says 110 million years carved into that granite rock, and then standing out there in the bronzy material, there's today's mountains, and then above it, artistically, you're trying to show also mountains that existed. Again, pure fantasy for what they look like, but over on the left, the artist has put in volcanic eruptions because some of that magma undoubtedly reached the surface, but that's all been eroded away. So please, next time you're at the Visitor Center, get out on the terrace and make sure you have a look at this. It's a marvelous sculpture. And of course, then you're standing there looking at those very mountains. At the same time, you're looking at that sculpture. And I think it's a pretty cool thing, actually. Climate at this time. We've been talking about erosion destroying the mountains, but look at the climate. Now look over here on the left. When you see this reddish, we're calling it a paleosol. A paleosol means ancient climate. And if we go to full screen to get an impact of that red, what I want to do here is say, if that's an ancient soil, it says tropical climate, how would you know it's tropical climate? Well, here's the way we do things. Here's a shot from in the tropics, and you see there the modern road. You see it going through the red soil there, zone where the vegetation or the crops are being grown. And what do you see there? Is basically it's what? Rusted rock. You've seen the heat, the abundance of warm water. They're rusting the iron-bearing minerals. They're dissolving, leaching out, carrying away a lot of the other ones. So the way we figure out an ancient climate, like the photo we were just looking at there in Mission Trails Park, is we compared the chemistry of these things. And you take a shot like this and you say, what's the chemistry of these rocks? And you see all the elements are in it, and you look and you see the minerals that are in it, what exists, what's been corroded, and you compare that to your soil, like in Mission Trails Park, and when you find one, they're identical, then we assume that the temperature, moisture conditions at that modern site are the same as we see in the old rocks. The little saying we use in geology for that, and it's over a 200-year saying, is the present is the key to the past. Learn something in the present, recognize it in the past, and thereby interpret it. So, there you are. You were standing at Mission Trails 120 million years ago in fear of your life. Now here you are 56 million years ago, and look what you're walking through. My goodness, how much more of a change can you get? We're talking about very different worlds, so to speak, depending on what time you are here in Mission Trails Park. Well, let's move on now and look along this same road. And let me mention that road. You see the gravel road there along the bottom? This would be this one where if you park there at Jackson Drive, the parking lot at Mission Trails there, and you walk down the road, cross the Santiago River, and walk up that road, several of the things we're looking at tonight are shown there. And there is some of that red ancient soil. The bright red ancient soil we were looking at, that would be in the lower left of the image as you see it right there. It would be where the rain runoff cut along the edge of the gravel road and exposed that ancient soil. You see it here in the cliff on the right side up above the fence. And think about this. The whitish rocks up above are about 42 million years old, and they are on top of the red soil. Remember superposition? So the younger layers are on top. If that's 42 billion years old, then anything beneath it has to be older than that. Just another evidence of the fact we're dealing with ancient soils. Now, everything we've been talking about has been local, but now we've generated our own magma, we've eroded it back down, we've weathered it here in Mission Trails Park, but now a visitor from the east. Now we have a huge river bringing in gravels. We're going to bury this entire landscape with these coarse sediments and build an alluvial fan. We were looking last time at alluvial fans. Here we're seeing that, the third phase, if you will, the third sense of history here at Mission Trails Park. In full screen, to appreciate this a little bit here, here's our cartoon of what the world looked like. This would be 50 million years ago, 40 million years ago in San Diego. So where it says river valley up there, that would be going all the way into today's geography without a Gulf of California. That would be Sonora, Mexico. The river comes out there, it says alluvial fan apex there, the top of the orange. That would be like where San Vicente Reservoir is now. We talked about an alluvial fan last time in Death Valley. Well, an alluvial fan that builds into the ocean we call a fan delta. So you see the fan delta coming out over the shoreline, feeding sediments into, keep going towards the bottom of the diagram with the orange where it says submarine channel. There's a submarine canyon there. And then deep sea fan, effectively it's another alluvial fan, if you will, but it's one on the deep sea floor. So we have this very integrated depositional system, and we want to see what has happened to those, and particularly now, where's Mission Trails Park and all this? Well, it's buried. It would be above maybe the T in Delta there, just for scale, for where we are. Messy diagram, I know, but what I want you to visualize was all that orange that we just had. Look over to the lower right there, the first one of those big red arrows, and you see the name there, El Plomo. Plomo in Espanol is lead. There's an abandoned lead mine right near there, and that's where we have found bedrock that is here in San Diego as cobbles. So in other words, rivers running from El Plomo towards your left, towards the west. Well, now, with the opening of the Gulf of California, look at the intermediate red arrow now. Come up across the border to where San Diego is, and you see a river and alluvial fan. And that would be going like from Lakeside to La Jolla. And then look offshore, another big set of faults. Up there, the highest of the three red arrows, and colored are Santa Cruz Island and San Miguel Island. Well, there's where the submarine fan is. So in other words, what was a neat east to west system drawn in orange there that we put together, it has been dismembered in two major offsets here since the time that it formed. Now let's look at the rocks that make this so unique. Now, up on the top there, you see in the upper left, it says Poway conglomerate class. We talked about rhyolite class. I showed a picture of those things the first week. And you see that distinctive texture with all those salmon-colored potassium feldspars and that unique rock. The piece on the bottom, as it says there, that's bedrock I broke off with a sledgehammer from mountains in Sonora, Mexico. The one on the top is just a class like most you have in your backyard. This is one I picked up in, well, today it's the site of Dale Elementary School, but it's just from San Diego, and you look at it and you see it looks like the same rock. We compared the chemistry of these things, trace element chemistry, and showed that they match, and these rocks and the chemistry they contain are what allowed us to draw that big orange continuous depositional system that we showed. So in just a general diagram, here's a lot of the shape of what was covered by that alluvial fan. And on the right-hand edge, it's very ragged because around the area of Highway 94 on south, those rocks are younger and they bury the alluvial fan, so we don't see it all. But we see poking up through it, as best of our calculations from today, would be everything's buried except the tip top of Cowles Mountain. And here's another one out on the terrace of the visitor center there at Mission Trails Park. And you notice in the upper left, 40 million years ago, snapshot. But you'll notice now near the upper right where the river, that's to be the 40 million year old river, comes out at San Vicente Reservoir. And you notice there how the artist Brian, how he's made it very rough near the head there, near San Vicente Reservoir, how the gravels drop out. Remember the alluvial fan in Death Valley last time? Where there was gravels at the head of the fan, then sand, and then when we got far out across the road, it was muddy and it was even landsliding. So he's put that into the diagram there where the sizes of the grains within the model there get finer just like they do in real life. Now we have labeled on there Oceanside and Chula Vista. Of course they don't exist 40 million years ago. We just put those there to give you a feel of the size, the area covered by that alluvial fan way back when. So let's take a little trip now. So here we are at the head of the alluvial fan in Lakeside. You know how you drive the freeway there, Highway 67, and just before you get to the San Diego River, it turns into a two-lane road? And as you're going that two-lane road, you see ahead of you these quarries. And you see those giant boulders? That's the head of the alluvial fan. Let's go to the west now and look at this alluvial fan, or parts of it are exposed in San Diego, all the way to the coast. So here's Mission Valley. The walls, we have to look at these fast because thousands of apartments are being built to cover these up. But that's all part of that alluvial fan. If we continue farther west, here we are at the beach, Black's Beach. That's Submarine Canyon. And to get the submarine fan, here we are up on Santa Cruz Island off of Santa Barbara. So there we have put together that whole system. Now, that's the big alluvial fan from the east that buried everything, but let's talk about other things now. What's the climate at that time? Do you see this diagram right here? Or excuse me, diagram. This is a photo I took. And you see this in a number of places in the western side of the park. Do you see those little vertical tubes that look whitish and sandy? What those are former roots. The organic material has been destroyed, but the root holes, if you will, have been filled with caliche. Now, caliche may not be a familiar word, but think in your house. When you go to the water faucet in the kitchen or in the bathrooms, there's usually some white salts crystallized around the head of the faucet. That's caliche. That's the same thing here. So to leave that caliche in the rock here tells us that the climate was such that evaporation was greater than precipitation. So we're looking at a semi-arid climate. Same place here, Mission Trails Park. We just were in the tropics 56 million years ago. Here we are 42 million years ago, and we're in a semi-arid climate. So climate does indeed change when you view it over geologic timescales. And there also in the west, you see some of the whole hills just look whitish because there's so much of that caliche that precipitated out in those rocks as the rainwater was evaporated out in that hot climate. And who was alive there then? Now, we don't have these fossils from Mission Trails Park, but in the western end of Mission Trails Park, I wouldn't be surprised to find something like Eohippus. This is one of the early horses. Horses used to be quite smaller. They've gotten larger through time and changed into the animals you're so familiar with, but those were there or in this vicinity at that time. And here's Gastornis. They called it the terror bird. As ferocious as it looks like it actually was probably a herbivore, and all that big beak was used to mash up very hard to chew vegetation. And what doesn't show in that image is it actually was taller than an adult human. Think more like the size of an ostrich. So there's a lot of cool fossils that have been found within the Eocene rocks, these age of rocks around San Diego County and throughout Southern California. Well, we just simply haven't prospected or found them in Mission Trails Park. But keep your eyes open when you're out there in the western part of those trails. If you see a bone or something sticking out, please notify the rangers, and let's get the paleontologists from the Natural History Museum. Let's get them out there and excavate. And gosh, I hope we do find some bones. That's an exciting thing. It's an exciting thing by itself, and then it's always cool to have more data, if you will, for understanding what the conditions were back at that time. Okay, let's move on now to the fourth phase here. We're back to erosion again now. The river bringing all those conglomerate clasts, all those rhyolitic clasts to San Diego was cut off, not coming here anymore. So that means without something being added to the surface, we simply erode the surface. And here in this beautiful, let's go full screen on this here. Here we are near the Grinding Rocks Trail here in Mission Trails Park, just north of the Visitor Center. And what do you see here? Physical disintegration of the rocks. Look how the tree roots are wedging apart and breaking the rocks into smaller pieces. This is a highly significant thing worldwide. And remember our principle about how things get done geologically? Small changes over long lengths of time. So in your mind, think of how many roots are going down into rocks around the world, and then multiply that by millions of years, and you see a lot of rock destruction. We also destroy rocks chemically. Now here we are back in the quarry with the fresh rocks like we were looking at, but let's look at these same rocks now in Mission Trails Park where, well, maybe I'll call your attention first to the upper right-hand part of the photo where it looks a bit reddish, it doesn't look so nice and neat. Well, those upper layers are what we see in Mission Trail Park, and if we walk over there, here's those same layers. Now look at them, rusted, chemically decomposed. So when we talk about wearing down the mountains by erosion, well, the first step is weathering by physical disintegration, like with the tree roots. And secondly, it's the chemical decomposition, where acids and all in the waters flowing through the rocks dissolve them. As you see here, here's those hard rocks being dissolved into weak material ready to be and easier to erode. Here's just the work of gravity itself. This is a view from the terrace here at the visitor center. You look up on South Fortuna Mountain, and what do you see here? You see that talus pile. Look at all those hunks of rock that have been brought down solely by gravity, nothing else. Gravity does a lot of work all by itself. And gravity also pulls the earth apart with landslides. What I'd like you to notice here is up at the upper right, where it says crown, and then it says headscarp. You notice there's kind of a circular amphitheater, and then below that headscarp it says head. Well, let's look here in Mission Trails. There's a lot of these. I've put orange over that to show the amphitheater at the head of the landslide, and then the orange arrow is showing the body of the landslide. You see the irregularities on it as it's being pulled downhill. So there's the work of gravity, pulling down blocks of plutonic rocks and pulling apart via landslides some of the sedimentary rock areas in the park. Now, another major thing about erosion we want to get into, but first what I want you to do is look at this inked drawing of the topography of San Diego, drawn about 1942, when all this geology we're talking about wasn't known. But towards the upper left, can you see that in the fine ink work of the artist's hands, can you see the remains of the Eocene alluvial fan, the big fan delta we were looking at? Let me cover it with a veil here. And now let me remove that veil and look there and see, can you see the difference in the grain of the topography? So there is the alluvial fan, and right beneath the pinkish triangle is a big white broad area, and it says Linda Vista Mesa, and then continuing down the lower right, San Diego Mesa. And I mean, that's probably one of the most typical topographies in San Diego, isn't it? The mesas. So what are the mesas? The mesas are uplifted seafloors. And what did this look like if we were here 1 million years ago? What would that area look like behind the pink triangle and below it there on Linda Vista Mesa? It would look like this. This is a beautiful one, what we call a marine terrace. It's an erosion platform. And you see over there on the left in the cliffs, you see all the fine layers of limestone and shale. That's about 200 million year old blue lias in Wales. But look what the waves have done. Look how they've come in and chopped into those cliffs. They've not only cut the cliffs, but they've smoothed it off to make that erosional terrace. Well, there we are in Wales, but how about visualizing that and saying, well, there's San Diego Mesa. There's the mesas in San Diego. That's how they formed. The thing on the left could be our big alluvial fan, Poway alluvial fan. Then the thing on the right would be the mesas of San Diego. So if we go back to that again, and I'm going to draw a blue line there and say, there's where a 1 million year shoreline would have been, where sea cliffs would have been. And I label that up at the top, 1 million year shoreline. And of course, what we're familiar with is over there in the left, the yellow. What we're familiar with there are these sea cliffs that we see here at Torrey Pines. But what I want to say right now is, take that cliff in your mind, hold that in your mind, hold that image, and let's go back. Now put that cliff there where the blue line is. Now, it's just to the inland side, the east side of Interstate 15, but it's hard to see up close because it's been eroded a lot. What I would like you to do is Mount Soledad down there in the lower left. The next time you're up on top there, look out over the mesa, over Miramar Marine Air Station, across I-15, and where that blue line is, and I said those were the sea cliffs. You don't notice the gullies as much then, but you can definitely see and feel those sea cliffs. So again, here's erosion. Took away a whole lot of that alluvial fan, cleaning up the area for us. And then, of course, running water. Here we are, running water. The work of that has cut Mission Gorge. And what do we have now? We're now here at the modern topography, if you will. And I repeat, or go back to where we started at the beginning. When we're looking at these beautiful mountains here, remember, they're all plutonic rocks. You're looking not at the mountaintops of today, were the mountain insides of 100 million years ago. So what we're looking at a tremendous amount of erosion. Where we see white clouds and a beautiful blue sky up there, we wouldn't have been seeing that at all. That should have all been mountain. And that's back 100 million years ago, 120 million years ago. And if we were here 45 million years ago, we wouldn't be seeing that blue sky and clouds because it would all, the topography there would have been buried by that alluvial fan. So what do we have then? Here we have, I'm going to say, Quaipai restored. A mountain had been buried for almost 25 million years, stopping the erosion, slowing it down. We've cleaned off the gravels off of the top of Quaipai, and here we've brought back an ancient topography. The official geological term for that is exhumed topography, where you've dug it up and the past is now restored to be the present. So there you have it. Again, the view from the Mission Trails Park Visitor Center, and should you be so inclined, they have things for sale there, but this isn't a commercial here. We're back to the view, the beautiful view of Mission Trails Park, and the sooner we can all meet together there, again there, the better. It's one of my favorite places to be, and I look forward to seeing each of you there at some point. Thank you very much. If there are any questions, we'll be happy to address them now. Well, that's a good sign. Everybody had grasped everything I said, so this is a rare event. I'm very appreciative. Oh, well, Gordon cites, here's a PhD in geology, one of the scientists who's contributed greatly to our knowledge of the earthquake history and how things have happened not only here in our region, but throughout Western North America. So thank you, Gordon. I appreciate that. Oh, yes. Oh, well, you know, what we're talking about here then is with the asthenosphere, I said it's don't visualize it as a brittle solid, but it's a solid that deforms or flows. You know, like, so then since it's so deep below the surface, we don't get to see it that much. So these are the ongoing debates all the time. What we're doing are things like, well, kind of like what they do in the medical offices now with the images of your body where they scan them and see what's going on in your insides. We use seismic waves to try to see what is going on inside the Earth. So there's a lot of debate about what goes on in the asthenosphere. And for that matter, the asthenosphere is just an upper layer within the mantle, and we don't really fully understand all the different things going on all the way down through the mantle. By that I say, you know, when I'm at something like a Geological Society of America meeting and I sit in on one where they're talking about all their tomography, what they have determined about the inside of the Earth, there's some very interesting papers, some things very well explained by people, but the interesting thing is almost none of them agree with each other. In other words, it's still a very open area for thinking and understanding. The chemicals that cause the Earth to rust, well, the most abundant one right away is rainwater, because water falling through the atmosphere dissolves CO2, and that's a weak carbonic acid, and so that is an acid. The plants themselves, a lot of them exude acids of various, or organic acids of very different types. And as you begin to decompose some minerals, you can release other things within it, like release sulfur. Sulfur can combine, you can make some sulfuric acid. In other words, given time and weak acids, not things that are going to take the skin off your fingers, but things that over time can do a lot to dissolve away. But the one that's always the most visible is, frankly, just rust, because iron is a very abundant element even up in the Earth's crust. It's one of the most abundant elements. And when you see rocks colored purplish, reddish, orangish, or yellow, odds are, though, that is oxidized iron. And the differences in the color depending on how the iron is complex, whether it's with, simply with oxygen or H2O or bicarbonate or, whatever, however it's complexed. Iron is the big coloring agent in rocks that are decomposing and weathering. In East County, yes, we do have some volcanic necks. So let me mention here, so if you have a volcano like this, and a lot of those things that explode and the stuff that comes down on the volcanoes are just debris that has fallen, so it's very weak. But in the pipe in the center where the magma came up, that may be solidified hard magma. So you can erode away the loose rock of the volcano cone, and then you have this neck of solid rock still sticking up. Now, we do have some of that in Jacumba Valley there. In two instances that John mentioned I mapped, a long time ago, where there was two things that we called volcanic necks there. In other words, the feeders inside volcanoes. The volcanoes there in Jacumba Valley are much younger. Those are Miocene age things. We're down in the 15 million year range, things that we don't have in mission trails, and I haven't mentioned any of the local geology that, well, unless it impacted directly on mission trails. But yes, we do have it. That's a good place to go out to see a lot of volcanic rocks, really, is the Jacumba Valley area. Yes, indeed. For anybody living in Tierra Santa, San Carlos, that this whole region right there, the cobbles in your backyard, almost all of them are from that Eocene massive alluvial fan we looked at. And the heck of it is, even though we erode a lot of that over time, a lot of those heavier cobbles don't disappear. It's kind of the finer stuff gets taken away, and a lot of the cobbles still hang around. Even if the rocks are younger, they still have those clasts within them. They get preserved or, well, recycled, I guess would be the term, recycled. So it's hard to own a house within that whole area of covered by that alluvial fan where you're not going to be digging up those cobbles in your yard. Well, Mount Woodson, that's stunning. Stunning when you look at Mount Woodson and you see all those huge, rounded, semi-spherical boulders of plutonic rock. And again, the other place that's so stunning is when you drive Interstate 8 and you've gone through Jacumba Valley and you're going to wind your way down to the desert floor. You're going through those same kinds of things. They're like nature's sculpture garden. And the way those things form, though, is not as exciting as they look. Rocks tend to break into three mutually perpendicular directions, make rectangles. Water seeping below the surface through the cracks will dissolve away on the surface. But at the corners, you have water dissolve away on one side, and the top, and it erodes away, eats away the corners of the rectangular block. Then when that material is washed away by rain, you're left with these big spheroidal boulders. So they're beautiful things to look at, but they form below the surface, groundwater, chemically decomposing, dissolving away the rocks below the surface. How long does the Santiago River run through the gorge? You know, I put a hypothesis about that into the book on mission trails geology, and I haven't had feedback yet from colleagues to know whether they go along with what I say or not. But I did it in some detail in there, but let me do this. Here's that big Eocene alluvial fan again. And if you can remember back even on the processes when we did last time, I showed that big Chinese alluvial fan. You see the blue water running in rivulets down one side of the fan, and the water runs down and gets gullies in different parts of the fan. Well, the Santiago River through Mission Gorge lines up with where you would have gullies on the remaining portion of the Eocene alluvial fan. So I basically think that during the erosion of the fan, which began 34 million years ago, the water running off from the east, some of that got into those, as the fan wears down, got into some of the gullies on the fan, occupied them, and then cut that path through Mission Gorge. So that's the way I visualize it, but like I said, I haven't had feedback from people yet to know whether they like that concept or they have a preferred explanation. You know, a place to see a whole lot of geology is that road I already mentioned. Parking there at Jackson Drive and Mission Gorge Road, walk down the road across Santiago River. Then on your left, there's those weathered Santiago Peak volcanics I was talking about. Then in the gully along there is that bright red Paleocene paleosol. Then there was that little fence with the reddish soil with the younger white stuff on top of it. Then over on your left is that big landslide I showed being pulled away. And now if you keep walking on around in the road cut there, you'll see where those caliche-filled root casts are. But please, please, They are very fragile. Look at them, photograph them, but please do not touch them or they will crumble and fall. Well, Hawaii is in great shape for rusting, if you will, because those basaltic rocks are extra rich in iron. So they're loaded with iron to begin with. And of course, you have a rainy climate for much of that area. But forgetting the rain for the moment, just think about how much of the volcanic eruptions or disturbance, if you want to say below ground, you send hot water up. You send hot water up, hundreds of degrees temperature, you're going to accelerate the chemical decomposition or the rusting process. So Hawaii is a perfect place to make those kinds of things. You know, in a very broad sense, I'm going to move from iron to aluminum. The aluminum ores of the world come from soils like this, where the weathering, the chemical weathering is so intense, you've removed almost all the other elements and left behind are enriched by subtraction. That is to say, as the other things are removed, the relative percentage of aluminum gets higher and higher. So that works for aluminum in terms of making the world's ore deposits, and it also works for iron as well. The quarries in Mission Trails Park are relatively recent, and it comes from a very sorry episode in recent history, to be blunt. 1950s, 1960s, city's not that big then, and people wanting crushed rock aggregate for construction, which you need, just simply went out and just took advantage of the topography and say, what are the parts that would be easiest to blow apart? It would be on an environmental scale of 0 to 100, where 100 is an A+ score. These folks would fail. They just pillaged the landscape, blowing it up to get out broken rock as cheap as possible, leaving all kinds of scars. Manganese dendrites are fascinating kinds of things. Maybe some of you have seen these things. You'll see them a lot in fractures in rocks. Like if here's the rocks that fractured and here's a fracture surface, kind of a planar surface. And you'll see things in black that almost look like ferns. They look like they're organic, the way they appear in terms of their shape and form. Well, actually what they are manganese rich. Here we are back to this chemical weathering again. We were just doing iron, and then I threw aluminum into the mix. Well, now let's do some of these things that are iron rich and also manganese rich. And then it's in the water, they're dissolved, and it precipitates out along little fronts. So along the front, you'll precipitate out some, and it grows, and it grows, and it grows out in these delicate fern-like structures that look like fossils, it looks organic, but it's just inorganic reprecipitation of dissolved or ions removed from dissolving rock. And age, they could be any age, because it's water running through rocks, dissolving and reprecipitating has been going on forever, so it could be darn near any age. Well, the clay soil in San Diego. Now we have some very clay soils in some places. Those are some of the areas that are very clay rich, are also the areas where we get landsliding during heavy rainfall intervals, during El Nino intervals and all. For those who are around San Diego for a long time, if you can remember the early 1980s, where it was landsliding galore, Rancho Bernardo, Poway, Santee, El Cajon, Fletcher Hills, Tierra Santa, all hills sliding all over the place, and those were where the clays were. So in this topography that we had, there are areas of San Diego that were accumulating clays. Now, I have focused heavily here on the alluvial fan because it buried all of Mission Trails Park. But off to the side of the fan, they're both in the model that is on the fence there at the visitor center, and in our diagrams to the sides of those, having a big alluvial fan come out means there's low areas next to it. And in those low areas, call them dry lagoons, things that are wet and dry, or if you could think back to that alluvial fan picture we looked at in Death Valley, where the alluvial fan built out and it was whitish salts and all around it in a lowland. Those are the areas, those flattish areas like that are alternately wetted and dried. That's where you tend to get most of the clays. And one within this same region as Mission Trails Park that's very significant, we call the Friars Formation. It's kind of a greenish, clay-rich sediment. And you'll recognize it with the kind of thing when you walk through it, you pick your shoe up and your shoe's caked with mud, there's those clay-rich sediments. So they form by chemical decomposition of rocks, but the biggest piles of it we have around San Diego are areas where they accumulated within these alternately wet and dry lagoonal areas. Grasslands east of Fortuna Mountain, the grass is particularly like not hard rock, but sandy, clayey soil that's easy to grow in, and a lot of that is the San Diego River sediment, the stuff that's on the San Diego River floodplain, sands and muds that were deposited there over the years, and so it's the kind of an area that if you were going to farm to grow some kind of a grain crop, those are the same areas you would pick. Chemical erosion mission trails caused by human behavior. No, most all that chemical erosion is natural. The biggest erosion by humans there would be physical things. And they built horse trails, which basically I don't think I've ever seen anybody use them, but not trying to make enemies here, but mountain bikers, when they're roaring along and cutting and turning, they're tearing up the soil. So it's more that physical destruction of wheeled areas. And you can tell also on the trails where we walk all the time, where you get hundreds of feet, over the month, and it goes time after time after time. So most of the erosion within, the human-caused erosion within Mission Trails Park is physical from bike tires or soles of shoes. Dictionary Hill is made of, for those who are not familiar with that, Dictionary Hills would be between south of Lemon Grove and before you get to National City, Chula Vista. It's a hill of the same kind of rock as Del Cerro, the same kind of rock as the Otay Mountains, the same kind of rock that we see in Mission Gorge Quarry. It's that Santiago Peak volcanics, those explosive fallout from volcanic eruptions. So Dictionary Hill would be a tough one. You're not going to have cobbles there when you're digging in your yard. Your problem there is going to be it's hard rock and it's hard to dig into. I used to know the answer to that. What is the word asthenosphere? It's a Greek root, and that's not coming into my mind at the moment. Lithosphere, hydrosphere. I got a bunch of those spheres, but astheno is not coming up at the moment. Oh, what animal character? I like ties. This one I picked up on I don't know, for those who are familiar with Mexico City, the Sanborn's drugstores, I picked this up on a tie rack on a counter in a drugstore in Mexico City. So the white things look like some deer-like sort of a form, and the orange I think is just, well, the reason I pick ties like this is a scientist talking to a crowd, we have a hard time keeping attention. So that's part of the reason I usually wear things like colorful coats and ties that sort of catch the eye, because I need all the help I can get to hold an audience. Is that? Well, yeah, there is a book available. It's a geology book, and I took the works of a lot of other people, plus a lot of original work I did, to put it in a book for not just for geologists, but for hopefully anybody who wanted to learn more about the geology of the park. And the book is given to the foundation. So every dollar that is spent for a book, 100% of that goes to the foundation. So again, thank you very much. I've enjoyed your interest in this series, and again, I look forward to seeing you at Mission Trails Park sometime. Thank you.